Hello everyone. Today we have the pleasure to host Bobak Kiani, who will talk about equivariant polynomials for graph neural networks. Bobak is a postdoc at Harvard University in the Applied Mathematics and Computer Science department. Before that, he got his PhD from MIT and studying electrical engineering and computer science. And his research is related to machine learning and quantum computation. His work focuses on the limits and capabilities of algorithms, especially those related on quantum machine learning. On the classical side, he's interested in theoretically studying the role of geometry and symmetries in learning algorithms. Thank you so much for accepting our invitation, Bobak, and the floor is yours.
Thank you so much for inviting me. I'm really happy to be here and present this work. Let me just say beforehand, I spoke with Farzan. I think people here, I understand, come from a tensor network background. And these slides, and also I think there's some quantum experience. These slides are related to a talk in purely classical machine learning, but feel free to ask any question and deflect or move away from the topic of this paper. I'm happy to keep this a discussion. So the topic I want to give today is related to equivariant polynomials for graph neural networks. I will give some introduction and all, but before I begin, I just want to say thank you to my collaborators, Omri, Derek, Hagai, and Yaron, and a big thanks to Derek, who I stole many of these slides from. Okay, so let's just take some background and some setup. In graph data, we often are given tasks that come in various forms. So, for example, on the left, we have a graph level task. Here, we're given a graph, and we want to predict, say, a number. Here being the toxicity. We may have node level tasks. These tasks, for example, may require us to fill in the color of a node. And we may have edge level tasks where we have to, maybe give edges that are missing. These graphs mathematically can be written as functions from Rn squared to R or Rn or Rn squared, depending on what you're predicting. So if you're predicting a graph level task, we have a function from Rn squared to R, and we say this is like a classification or a regression. And similarly, for node level tasks, we have to predict n numbers or whatever it may be. The big important thing with graph data is that these tasks have a symmetry. And the symmetry is, in the machine learning literature, is termed an invariant or equivariant function. And on the left, this takes the form that essentially, when we want to perform any prediction or classification or regression or whatever task it may be, it doesn't matter how we label the nodes in our graph. If we were to permute the graph and the adjacency matrix of the graph, the function should be the same. Similarly, for node level tasks, if I decide node 1 is now node 3, I should also permute the output of my function so that whatever I said for node 1 now becomes node 3, and it should have this, what we call equivariance now. And again, for edge level tasks where we have to output data on edges, we have a similar equivariance. Just to be very precise and give an example, like this graph here is written in 3 different ways. These are what are called isomorphic graphs. And the basic message is that no matter what way I give you this graph, my machine learning model should output the same answer for each of these graphs. Or in the case of a node level task, it should permute the graph accordingly based on the equivariance property of this. Okay, so I will go into now equivariant polynomials. These are an instance of polynomials that have this property that I just described, that they have this symmetry that allows us to do learning. And on top of that, they will be polynomials, so they'll have a very simple way of writing. But before I jump into that, I just want to give one fact of why do we care about polynomials in machine learning. And I think they come up both as a proof technique and as a tool for application. The basic message is that polynomials are expressive in a universal sense, meaning that if you have any compact domain and you want to approximate a continuous function, there's always going to be a polynomial that's within an epsilon error of that true function, that function f. This is, you can take whatever norm you pick. Like here, for example, you can take the inf norm, sorry, the sup norm. But here, it's just a very general statement. If the words are confusing, just think, I have a continuous function I want to learn, and there's always going to be a polynomial that's close enough to this continuous function. A similar story holds true for equivariant polynomials with some caveats. So this is what I want to say now is only going to be true for compact groups. All finite groups, which include the group of permutations, are within this setting. For non-compact groups, there's some subtleties that I won't go into, but for compact groups in a compact domain, we have a similar statement that you have an equivariant continuous function f. There's always going to be some polynomial that you can find, which will be within any arbitrary epsilon error to your target function. So stepping back from the math, just high level, if we can categorize and work with these polynomials, in some sense, we've made a universal architecture because we can basically approximate any function we'd like. And if we can manipulate these polynomials in a good and clean way, then we work with polynomials and we're universal. Here's an example of this where this story works out very nicely. And we'll find that this example is rather a special case. In general, this story will not be as nice as this, but consider the permutation group with its standard representation. So here by standard representation, I just mean you have inputs which are in n numbers, and the group acts by just permuting those n numbers according to the permutation itself. This is what you would think of as a standard permutation. And we know that one way to represent any invariant polynomial is to construct polynomials on top of the power sum polynomials. Now that's a lot of words. Let me just pause for a second to explain this. So you'll see there's this function g theta. We can take this as a neural network for now. And it acts on n different inputs, which are sum of xi, sum of xi squared, sum of xi cubed, and so on up to sum of xi to the n. And if you were to just feed these n polynomials into your network and then ask the network to manipulate anything on top of this, this would be a universal approximation. And this is nice because, if you want to do any symmetric function, you can just figure out these n different polynomials and then feed this into whatever architecture you like that's universal and proceed. The story, though, gets much more complicated when we don't have the standard representation. And note that graphs are an instance of this. Here, the representation acts on matrices, and you have to permute the rows and column of the matrices at the same time, and we no longer have this nice picture. In fact, if you were to have such a nice picture as before, where you could enumerate a basis of all these polynomials, you would solve graph isomorphism efficiently, which people don't believe we can do. And I think if you were to figure that out, that'd be a big result. And yeah, anyway, so we don't expect to be able to have such a nice story when we have a different representation. So I guess just to summarize this example, if we were on the right-hand side where representation is just the standard representation, we're good. But on the left-hand side, we have representation, which is like a tensor product that acts on both rows and columns, and the story is a bit more complicated. But all is not lost. We don't have to work with a generating basis of polynomials. We can also work with a spanning basis. So what is a spanning basis? A generating basis is like what we said before. You can construct any polynomial as a set of products and sums of these possible things. But in a spanning basis, we literally will linearly enumerate all possible monomials in Symmetric cases, these won't be monomials, they'll be actual polynomials, but a spanning basis is a linear basis of the set of all possible polynomials, and in the invariant case, it'll be a linear basis of all possible invariant polynomials. There's one slight challenge with this, which is that the spanning basis is arbitrarily large. So we have to choose some set of polynomials to work with, and that is going to be the focus of what follows. Hopefully I haven't confused people yet. If there's questions, please feel free to stop me and ask. But if not, I'll proceed assuming we're all good. Okay. So a couple applications of this. Application one, why would you want these polynomials? Well, if you have a GNN architecture that cannot compute a polynomial, you could add that polynomial as a pre-computed feature and make the GNN potentially more powerful. We can also potentially integrate the polynomial into the architecture. For example, you can add a matrix transpose to your architecture, and this is done previously in PPGNs. But just an example, if we have a sense of what these polynomials are and we know that a GNN can't compute it, we can potentially make our GNN more powerful by leveraging it. Similarly, it gives a measure of expressiveness. And here, this is a way of saying a GNN or a given architecture is degree D expressive if it can compute all possible degree D equivariant polynomials. And this is a bit different than previous measures of expressiveness. And those previous measures are a bit coarser because, well, the jumps between, something like one Y-Sphile element to two Y-Sphile element is rather big, and most GNNs end up falling within one class and so on and so forth. So this gives a more refined notion of expressiveness and a way to separate architectures. And as we'll see later, there is a connection to Y-Sphile element, but let's just set that aside. Okay. So that was all set up. Let's describe how we actually get these equivariant graph polynomials and how to construct them and how to calculate them. This will be once you understand the algorithm, it'll be a rather straightforward procedure. So bear with me for like these couple minutes as I go through the procedure, and then hopefully it'll make sense with a couple of examples. Previous work has shown how to do a basis for invariant polynomials. Here, invariant is what I said earlier, which is a graph level task. You have a function from, let's say, an adjacency matrix to a number, and you want this to be invariant to permutations of rows and columns. And a basis for any polynomial of degree D corresponds to a directed multigraph of D edges. Here, a multigraph means you can have multiple edges going between nodes. And let me describe how this works. So any possible polynomial you'd want to write in this basis can be attached to a graph. And if you can understand how to take this graph and construct the function, then by just enumerating all possible multigraphs, we have a complete understanding of what the equivariant functions and invariant functions are. So let's do this. So how do we go from a graph to a function? We label nodes. We follow three steps. First, we label our nodes arbitrarily. So we have I1, I2, I3 here. Then we sum over the nodes. So you'll note that there's a sum now from I1, I2, I3 equals 1 to n. And then we take in our summand all possible terms that correspond to the edges. So you'll note that there's one edge going from I1 to I2, so we have x I1, I2. And then we have two edges going from I3 to I2, so we have x squared I3, I2. And then one self loop here from I3, I3, so that'll be a diagonal entry x I3, I3. And simply put, if you follow this procedure, you give me a multigraph and you arbitrarily label it, and then do this procedure where you sum over the nodes and put these summons whenever you have an edge in the graph. Any possible invariant polynomial in your basis can be written in this way. How do we do equivariant polynomials? The procedure is very similar, but now we have to add a red edge, and this red edge will correspond to the output of our map. So here we don't have just one number we're outputting, we have n squared numbers we're outputting. You can think of this red edge as keeping track of what output you're looking at. So again, same procedure. Label your nodes. So here we have I1, I2, I3. Sum over all the nodes not in your red edge. So here we have just sum over I2. And then note that I1, I3 is in the output, so that's fixed. And then we put summons in the same way as before, corresponding to black edges. So again, the same summon that we had previously shows up here. And this is now an equivariant polynomial. For each possible value of the output, we have a polynomial that gives the value of that output. And in the same way as before with invariant polynomials, this is universal. Any possible polynomial can be written in this form. I will say there's another way to write this basis without repeating indices. So I1, I2, I3 can be also written as not the same index. You sum over all possible tuples where I1, I2, and I3 are not equal. And this corresponds to homomorphism counts, which are used in GNN. So homomorphism counts are like counting the number of triangles or the number of cliques or something like this. And there's a nice analogy to that when you do this summation over non-unique indices. Or sorry, over unique indices. Okay. So I think this is where we'll get into tensor network stuff. And I guess the overall message, which we'll see in this portion, is that tensor networks can be used to efficiently calculate these functions, which I listed earlier, which are sums over a bunch of polynomials. And the procedure overall is basically a tensor contraction. So you can write all these possible equivariant polynomial calculations as an einsum. This is a PyTorch NumPy thing. If you haven't seen it before, it's just Einstein summation with tensors. But you write out your polynomial, you put it in the einsum, and you make the indices according to what the indices were previously, and you just plug in your input x as your input to your einsum. And let me just give it to you in a clean way. So let's give an example. So in the below, we want to calculate this equivariant polynomial, which has these 4 edges. And previously, we showed that you follow our procedure and you can write out this polynomial as a summation over 3 different indices. And if you were to just run this sum over naively, you would have to sum over n cubed numbers because there's 3 indices and each of them runs from 1 to n. And doing that just arbitrarily will take n cubed time. But as you can see, this looks like a tensor network, and we can probably do this in a smarter way. So how do we do it? We start first with a summation that does summation over I4. Note that I4 factors out, and we can contract this node in a way to remove it from the computation. Sorry. My screen just got weird. Okay. Anyway, sorry, I can't see my screen right now. Can you guys see my screen?
Yes, you can see your screen if
Okay.
you.
Give me one sec. You're good now. Sorry. Okay, so right, so you can group these sums. You do I5 first, and then I4, and then I3, and this is like a tensor contraction. You are moving nodes according to some smart ordering of the contraction. Let's do this in a bit more complicated way. Here's a more complicated graph that we'd want to do this tensor contraction for. And on the top right, you'll see the target computation. And then I'll contract this in some order, and you'll see what remains on the bottom right as we contract this tensor network. So first, we'll contract I4. This will result in a self-loop being added to the graph. And then we have a new graph, which is now no longer has an I4 node. It has just 3 nodes now. Similarly, we'll contract node 3, A3. And you'll see now that we've added a Z to the graph, which is the result of that contraction. And then finally, we just group it all together. And this is our remaining computation, is just combining all the possible X's and Y's and Z's that we got in this. And we are now finished. We've calculated this polynomial for any I1, I2. And you'll see that this computation took order n squared time. This previous one was 1 isolated. This took linear time. It was order n time. Any such computation that corresponds to the tensor network, which takes linear time, gives you this one Weisfather-Lehmann expressivity. There's a nice connection to tree widths. If your tree width of your tensor network is equal to 2, or sorry, to 1, then if it's a tree or if it looks like a tree, then you will have one Weisfather-Lehmann. So let me say this in a bit more detail. On the left, we have a set of types of contractions we can apply here. You know, when you do the contraction, you're looking for parts of your graph that look like one of the elements of what's shown on the left. And doing this type of contraction requires order n space and order n squared time. On the right, we have a little bit more powerful things, which if you allow for contractions where the subgraphs look like what is shown on the right, then you get order n squared space and order n squared. Here, I just want to say that what you see on the left is one Weisfather-Lehmann expressive, meaning that if you allow contractions of the subgraphs that are contained on the left-hand side, then you will get one Weisfather-Lehmann expressivity. This goes back to the equivalence between tensor contractions of a given tree width and Weisfather-Lehmann expressivity. I won't say too much more about that. If you want, just ask me questions afterwards and we can talk more. But just for now, if you keep this in mind and you care about expressivity proofs, the stuff on the left gives you one Weisfather-Lehmann, the stuff on the right gives you 3 Weisfather-Lehmann or 2 folklore Weisfather-Lehmann, depending on how you pick your expressivity hierarchy. Okay. And just to give a sense of how relevant these polynomials are and what types of stuff that these things can do, many of these polynomials of a given degree end up being not expressible by the node or the edge featured. So the left-hand side was Fn here, the right-hand side is Fe. So even at small degree, I guess depending on how you read this graph, um, there will be some set of polynomials that we can't calculate using this type of tensor network contraction. And these polynomials will require higher order tensor contractions for this to happen, which won't be covered by these two classes. You can imagine generalizing this procedure to higher and higher order stuff, but this would require more runtime or more space, which, this paper had a practical lens to it. We wanted it to be efficient, so we didn't do this. But if you want to get a sense of how many of the polynomials you can actually calculate with this procedure up to a given power, we've listed them here. Okay, so that's the description of the algorithm and the equivariant polynomials. Before I go to experiments, is there any questions?
I have a clarification question. So the degree of
Yeah.
the polynomial, is it the
Yeah.
number of edges?
Yes,
So
yes. So let me go back to an example. So this first one, for example, will have degree 4. You'll note there's 4 black edges. And that's true. So if you have polynomial of degree x, or let me say degree k, then you'll need k black edges.
And these edges, they are not the edges of the graph, are they? Or they're just computational graph?
Can you expand what you mean by that?
So here you want to calculate a function that is from the graph, like the feature of the nodes of the graph to R. And here the edges are the same edges as these black edges, or the edges in the graph is different.
Oh, so the
So is
I see what you're asking. The graph, this graph has nothing to do with the graph you're actually computing the function on top of. The input
okay.
or the graph you're computing would be x. It's a you just treat it as a sequence, as a list of n squared numbers indexed by the adjacency matrix entries.
So you choose the edges arbitrarily here, these edges here.
In a sense, we sum over all possible nodes. So this summation will pick up certain edges in the graph input x. That makes sense.
Okay, thank you very much.
Good question. Is there a question in the chat?
No, it's not a question.
Okay. Okay. Okay, I will run through experiments now. So I actually didn't, I'm more of a theoretical person, so I didn't run these experiments myself, and I hope I can answer the questions that you may have with them, but I probably won't be able to answer the intricate details. But okay, so here we ran so here what we did with these graph polynomials is as mentioned earlier, we just attached them as node features. So we calculated these various polynomials up to degree 5 and 6, and we appended them to the input node features of the graph. So when you see ppgn plus parentheses 5, that means we calculated all the possible degree 5 variant polynomials and appended them to the node features of the graph. And what you'll find is this gave a little boost in the performance of the model. This is for zinc, Fool, and alchemy, which I think are 2 molecule data sets that people use as sort of a benchmark in GNN tests. Similarly, we tried this over other architectures too. So this is gated GCN, which is a graph convolutional network. And we added these polynomials in the same way as before. And and it improved the performance of the model. It gave more information for the model to learn on, and you can see that improvement went from like 0.265 to 0.1 on this Zinc 12K data set. I will say that this procedure may seem expensive, but it's actually much faster than previous state-of-the-art models. So Graph GPS is a graph transformer model, which I've been told is very expensive, meaning it takes a long time to train and to run. And this is an order of magnitude faster than this, and it achieves similar results to Graph GPS. So, I think the takeaway I take from this is like maybe, take a efficient and fast run architecture. And if you want to just try improving the performance a little bit, consider adding these polynomial features to the input of the data set. You can do this pre-computation once, and it may result in a significant improvement in performance. And you'll see, for example, like adding the computing all the 7-degree polynomial features for the entire data set took 310 seconds, which is an order of magnitude less time than the training time. So this is in general probably an efficient procedure. That is all from me. I'll stay back and answer questions, but let me stop my sharing for now. Thank you again for having me.
Thank you, Bobak, for the nice talk. I had a quick question on this experiment. So where do you add the polynomial features? Because some of these polynomial features, they are product of, if I understood correctly, right? They are product of features coming from different nodes. So how does that work? Is it that you concatenate those polynomial features on all of the nodes? They get some part of the node feature that is actually the same, that is shared between all nodes, and that are those pre-computed polynomial features?
Yeah, so it's a twofold procedure. The first step that we do is we first check which of these polynomials in architecture can actually calculate. If it can't calculate it, then we construct a list of the ones that can't calculate it up to degree D. And then we have node equivariant or edge equivariant features. So for the concatenation, if there's edge features in the data set that matter, we will calculate the edge equivariant polynomials. And for each edge, there will be like a polynomial that gives a new feature that we append. If they're only node features, then we'll only do the node equivariant polynomials, and we will, for each node, calculate that polynomial and append that to the features of the node, if that makes sense.
But so this means that some nodes will have the same features because these polynomials are shared across all nodes, no?
Some of the functions will be the same across nodes, but that's not a guarantee. That's not
Okay.
So if you remember, let me give an example. I'll share my screen again. It's a good question. So like take let me just go back to this example here. So this graph here, which corresponds to this polynomial, says that for the edge I1, I2, which this will be for any possible I1, I2, you'll have I1, I2 for all possible edges in your graph. You will have this function, which you have to calculate. Now, given a fixed I1, I2, this function may be different for another I1, I2, because just these indices are different. It's a bit, I think if you like write out a couple of these by hand, it starts making a lot more sense. I know it's hard to describe it in this just over a talk.
So one thing I'm trying to figure out is even if they are not the same, like so let's say here you will add edge features that are this new polynomial that you figure out your architecture cannot compute. Even though they will not be the same for all the edges, you're still guaranteed that there will be the same number of those for each edges. in such a way
Yes.
that your
So
edge feature now is still has the same dimension, basically.
perfect. Yeah, perfect. So right, for each edge that exists for each edge I1, I2, you will have an added number for this polynomial, one extra dimension. And if you, I don't know, say you have k such polynomials that you want to concatenate into your features, you will have an extra k dimensions.
Okay.
Yeah.
Okay. Thank you.
Yeah.
I think maybe Fadane got disconnected. Are you still here, Fadane? Fadane was moderating, right? So I don't know, are there any other questions? Ah, Fadane is back.
Yes, sorry, my Zoom is crashing these days. Thank you so much for a nice presentation. If there is not, if there isn't any more questions, maybe I'll stop the presentation.
Yeah, appreciate it. Thanks for having me.